One night the sky showed something it never had before, a second bright disk hanging beside the moon. People paused, phones lit, and the hush settled over streets. Astronomers recalled past sky surprises, like the bright 1054 supernova that blindsided medieval observers. Even a sudden comet in 1835 sparked panic, though its path was eventually charted. Villagers in the highlands gathered on rooftops, pointing upward as the twin lights swelled the horizon. Elders whispered old legends, wondering if the heavens were delivering a new omen. The new disk rose over city skylines, its outline crisp against the night, like a silent sentinel. Its surface glimmered faintly, a pale gray that differed from the familiar lunar glow. People on balconies lifted phones, capturing a twin glow that did not belong to any known satellite. The images spread quickly, each pixel confirming what eyes alone could not fully trust. In cafes, strangers exchanged startled glances, each wondering whether the image was real or a trick of the eye. A barista muttered about the moon's habit of keeping secrets while the espresso machine hissed on. The first tweets were simple, 2 moons tonight. No hashtags, just raw astonishment. Replies piled up, some asking for proof, others for meaning, all in the same breath. News anchors switched to live feeds, their faces flat as the second body lingered in the frame. A meteorologist, usually calm, hesitated before naming the object, aware of the weight each word carried. Scientists at observatories scrambled to point their instruments, eyes half closed from sleepless nights. Their spectrographs whirred, seeking a fingerprint that could tell if the rock reflected sunlight or glowed of its own. Their first question, does it orbit Earth, or is it a stray asteroid caught in a fleeting dance? If it circles, its period must match what they could measure against the familiar moon's rhythm. The answer required measuring parallax, a technique taught in school but rarely used for sudden sky shows. 2 telescopes, hundreds of kilometers apart, would need to lock onto the same speck and compare angles. Astronomers compared its brightness to the moon's, noting a slightly cooler hue that hinted at a different surface. The contrast reminded them of the way Earth's own clouds soften the sun's glare, suggesting a thinner atmosphere perhaps. Historical records of sudden celestial bodies were sparse, yet cultures often turned such events into omens. Those omens, written on clay or parchment, rarely mentioned a second moon, making this sight feel unprecedented. In ancient Mesopotamia, a bright star appearing where none should have been was logged as a warning. Scholars today wonder whether that entry could have been a misidentified comet, not a lunar twin. Modern societies lack a single priesthood to interpret, but we have panels of experts who speak in cautious tones. Their caution stems from a history of false alarms, when comets were once thought to herald disaster. The press quoted a senior astronomer saying, "We have never seen a second lunar object appear without warning." She added that the absence of any prior detection made the event all the more puzzling. She added, "Our models assume a single satellite, so we must start from scratch." Reworking equations in the middle of the night felt like trying to read a map in fog. I find it hard to picture how a massive rock could slip into orbit without shaking the planet. The idea of a silent insertion strains my intuition, yet the sky shows no obvious tremor. Some geologists whispered about hidden stresses, but the ground felt unchanged underfoot. Seismic stations reported only routine tremors, nothing that matched a sudden extra pull. The public, meanwhile, filled forums with speculation ranging from alien megastructures to secret government experiments. A thread titled Moon 2.0 gathered thousands of comments, each more elaborate than the last. A teenager posted a doodle of 2 moons smiling, and it was shared thousands of times. The simple sketch reminded adults that wonder can survive even amid scientific uncertainty. Scientists received a flood of emails asking, Will the tides be higher? The question felt premature. They replied that tide calculations required precise orbital data which was still being gathered. In the meantime, amateur astronomers set up backyard telescopes, tracking the new object's path night after night. Their logs noted a slow drift eastward, a motion unlike any known lunar libration. They posted nightly charts, inviting professionals to compare notes across continents. The data fed into global networks, where algorithms flagged the anomaly and sent alerts to research stations. These alerts sparked a scramble for telescope time, as every minute of observation became precious. A senior analyst wrote, "We must verify whether this is a bound object or a passing near-Earth asteroid." The distinction mattered because a permanent companion would reshape nighttime illumination, while a transient would fade soon. Yet the sky held its secret, the second disk lingering, stubbornly bright, refusing to vanish with the dawn. Even as the first light crept over hills, the twin remained, a stubborn reminder of the night's surprise. I don't know what will happen next. People simply watch, eyes glued to the heavens. The silence of the night feels heavier now, as if the air itself is listening. Orbiting satellites turned their cameras toward the Earth, confirming the second body from above the atmosphere. The images showed a faint halo of dust, suggesting the object might be surrounded by a thin veil. Scientists noted the halo's size matched no known lunar feature, raising more questions than answers. In the Far East, fishermen halted their nets, eyes fixed on the sky as the twin moons rose. Their radios crackled with a single word, impossible, before the night air swallowed the transmission. The moment lingered, a shared pause that stretched across continents, as if the planet collectively inhaled. By morning, a video conference linked observatories from 3 continents, each screen showing the same bright speck. Scientists spoke in low tones, aware that any premature claim would echo through global headlines. One researcher admitted, "We are still mapping its orbit. The numbers are not yet reliable." Street artists began sketching the twin moons on walls, their chalk outlines trembling in the evening breeze. A mural in a downtown alley depicted the moons as mirrored eyes, watching over the city. Passers-by stopped, stared, then moved on, their thoughts lingering like the faint glow above. On a balcony, a cat perched, its ears twitching at the faint, rhythmic pull of the twin silhouettes. Its tail flicked once, as if marking the moment the sky changed, then settled back into the night. The sudden appearance of a second satellite forces us to ask how it could stay aloft. Any orbit balances Earth's pull against the object's inertia. One way to preserve balance is to place the newcomer near a gravitational saddle point. Those points, called Lagrange locations, are where Earth's and the original moon's forces cancel. A small body can linger there if its mass remains low enough not to shift the point. The most familiar of these spots lies 60 degrees ahead of or behind a primary body. In that configuration, the second moon would be a Trojan companion, sharing the same orbit. For Earth, the same math applies, but the region is narrower because our planet is smaller. A Trojan moon would trace the same path as our familiar satellite, never catching up. It would also never fall behind, keeping a constant angular separation. The crucial factor is the new moon's mass, too heavy, and the shared orbit destabilizes. Rough calculations suggest a body no larger than a few percent of the moon's mass could survive. Anything larger would shift the center of mass enough to break the delicate balance. In a horseshoe orbit, each body spends most of its time on opposite sides of Earth. Saturn's moons Janus and Epimetheus illustrate this behavior with their regular swaps. If the newcomer approached the size of our moon, the system would likely become a binary pair. In a binary configuration, the two bodies orbit a common center of mass. That barycenter then travels around Earth, much like Pluto and its large companion. Their barycenter lies outside Pluto, meaning both bodies circle a point in space. That arrangement keeps the system stable for billions of years, despite the body's comparable sizes. Anything lighter would keep the barycenter inside Earth, reverting to a simple satellite case. Mass is not the only constraint. Orbital distance matters as well. The farther a moon sits, the weaker Earth's pull and the easier it is to share space. Yet increase the distance too much, and the sun's gravity begins to dominate. That limit is called the Hill sphere, roughly 1.5 million kilometers for Earth. Within that sphere, a satellite can remain bound if its orbit stays well inside the outer edge. The moon orbits at 384,000 kilometers, comfortably inside the Hill sphere. A second moon could occupy a nearby radius, perhaps 450,000 kilometers, and still be safe. However, if the two orbits overlap too closely, mutual perturbations will grow. Those perturbations can pump eccentricity, eventually causing a collision or ejection. Simulations show that spacing of at least a few hundred kilometers in semi-major axis helps avoid rapid chaos. The timescale for such chaos can range from centuries to millions of years, depending on masses. A light Trojan might linger for billions of years, while a heavy co-orbital could decay in a few thousand. I find it hard to picture a moon the size of our own wobbling in a horseshoe. The mathematics tells us the pattern would be fragile, like a tightrope under wind. Observations of Saturn's moons remind us that nature can maintain such tight configurations. Scaling up to lunar dimensions introduces new forces, especially tidal interactions with Earth. Tides raise bulges on Earth, which in turn tug back on the orbiting body. This tidal torque can slowly transfer angular momentum, nudging the orbit outward. For a single moon, the effect moves it away by about 3.8 centimeters per year. Add a second body, and the exchange becomes a three-way conversation. If the newcomer is lighter, Earth may give it a faster outward drift than the larger moon. Over millions of years, that could separate the pair enough to become independent satellites. Conversely, a heavier second moon could pull the original moon inward, accelerating its decay. We don't really know how those competing torques would balance in a real system. Another subtle effect is the precession of orbital nodes caused by Earth's equatorial bulge. This precession can lock two moons into a resonant pattern, preventing close approaches. A similar resonance could keep two Earth moons from ever colliding. Yet establishing such a resonance would likely require a gradual migration, not an instant appearance. That raises the question of how a second moon could appear without violating orbital physics. One speculative route is capture, a passing asteroid slowed by atmospheric drag or tidal forces. Capture usually leaves the object in a highly elliptical orbit that later circularizes. If the object were already moon-sized, its eccentric path would intersect the existing moon's orbit. Repeated close passes would either eject it or grind it down into debris. The debris could coalesce into a smaller companion, perhaps settling near a Lagrange point. This scenario mirrors how Mars' moons Phobos and Deimos may have been captured. Their irregular shapes hint at a captured origin rather than in situ formation. Yet Earth's atmosphere is thicker, making capture of a large body far less likely. Another route is a giant impact that throws out enough material to form a second satellite. Those clumps could accrete separately, each becoming a moon in its own orbit. Simulations suggest that forming two sizable moons from one impact is rare, but not impossible. Their eventual spacing would depend on their relative masses and the rate of angular momentum transfer. The mathematics is clear, but the initial conditions remain speculative. What we can say is that any stable configuration must respect the limits set by gravity and motion. It must also keep the center of mass within Earth's Hill sphere, otherwise solar perturbations dominate. In practice, that means the combined mass of the two moons cannot exceed a few percent of Earth's. Anything larger would shift the barycenter far enough to destabilize the whole system. Observations of other systems remind us that orbital evolution is relentless. In the end, a double moon is not forbidden, but it lives in a narrow corridor of parameters. I don't have a perfect picture of where that corridor lies for Earth. What we do know is that gravity, inertia, and tides together carve out a fragile niche. A tiny Trojan might linger for eons, while a heavyweight binary would reshuffle the night sky quickly. For now, the equations sit on a page, waiting for a real example to test them. Until we find one, we can only trace the limits with pencil and computer. One concrete observation: the Earth-Moon barycenter sits about 4,600 kilometers from Earth's center. Adding another moon of half that mass would push the barycenter beyond the surface. That shift would change how Earth's rotation couples to the tides. It would also alter the length of the day by a fraction of a second. Such a tiny change is measurable with modern instruments, if we ever needed to. I find it hard to imagine waking to two pale disks, each tugging at the oceans. Yet the physics tells us the sky could accommodate them, provided the numbers line up just right. The smallest detail that remains clear is the role of the Hill sphere as a hard boundary. The extralunar mass would sit opposite the familiar companion, its pull adding to the tide-raising force we already measure. In a simple lab note style, I start by recalling the basic tidal equation. The height of the bulge scales with the product of the moon's mass and the inverse cube of its distance. Double the mass at the same orbit would, in theory, double the contribution. Double the distance would cut it to 1/8. The new moon, if it arrived on a similar path, would therefore increase the total tidal potential by roughly 50%. I write the combined bulge as the sum of two sine waves, each representing one moon's tide. The peaks line up when the moons are in conjunction, producing a high tide that can be 1.5 times the normal maximum. When they sit opposite each other, the waves cancel partially, and the high tide shrinks to about 0.7 of the usual height. The low tide follows the same pattern, deepening when the bulges oppose each other and shallowing when they reinforce. To check the numbers, I compare them with the long-term record from the Port of Liverpool tide gauge. Over the past century, the average spring tide rises about 2.5 meters above mean sea level, while the average neap tide climbs roughly 1.2 meters. Adding a second moon would push the spring extreme toward 3.8 meters and pull the neap low down to about 0.8 meters. Those figures are rough, but they give a sense of the scale. I find it hard to picture coastlines coping with a tide that swings an extra meter every few hours. The intertidal zone, already a thin strip of sand and rock, would be flooded more often and for longer periods. Organisms that time their feeding and breeding to the regular rhythm would be forced into a new schedule. Some mussel beds might drown under prolonged immersion, while certain algae could gain a foothold where they were previously exposed to air. The change would not be uniform. Because the tidal force depends on latitude, regions near the equator would feel a stronger combined pull than those near the poles. In the Gulf of Mexico, the added bulge could raise the mean high tide by nearly 2 meters, while in the North Sea the increase might stay under a meter. That unevenness would set up new pressure gradients in the ocean, nudging currents toward a different equilibrium. I sketch a quick calculation of the new resonant periods. The ocean has natural modes, standing waves that amplify when the forcing frequency matches. The familiar fortnightly cycle of spring and neap tides already excites some of these modes. Introducing a second lunar frequency, half a month out of phase, would generate a beat pattern with a period of about a month. In certain basins, such as the Bay of Fundy, the beat could line up with the basin's natural resonance. pushing the tidal range beyond anything recorded in the past. Historical tidal records become a baseline against which we can measure deviation. The Greenwich tide gauge, operating since the 1850s, shows a slow rise of about 0.3 centimeters per decade, largely attributed to climate-driven sea level change. The sudden appearance of a second moon would dwarf that trend, producing a step change that would be unmistakable in the data. The challenge would be to separate the lunar effect from other signals, a task that would keep oceanographers busy for years. I note that the ocean's response is not purely linear. The increased amplitude would cause stronger friction against the seabed, especially in shallow shelves. That friction dissipates energy, turning some of the extra tidal power into heat. In places like the South China Sea, where the continental slope is gentle, the extra energy could be absorbed more efficiently, muting the surface signal but heating the bottom layer by a fraction of a degree. The extra gravitational pull would also tug on the solid Earth. The solid tide, tiny rises and falls of the crust, would be amplified, adding a few millimeters to the already measurable deformation. Those deformations could shift stress on fault lines, but the effect would be modest compared with tectonic forces. Still, the possibility of a small increase in micro-earthquake activity cannot be ruled out. I turn to the coastal ecosystems that depend on the rhythm of the tide. Salt marshes, for instance, rely on regular inundation to bring in nutrients and flush out waste. A higher high tide could push salt water further inland, altering the salinity gradient that many plants need. Mangrove seedlings, which sprout in the upper intertidal zone, might find themselves permanently submerged, reducing recruitment rates. Conversely, some species could benefit. Certain fish that spawn in shallow pools at low tide would have more time to lay eggs before the water returns. The expanded low tide window, when the moons are opposed, could create longer periods of exposure, giving shorebirds more time to forage on exposed mudflats. The net ecological impact would be a patchwork of winners and losers, varying from one coastline to the next. I write a quick estimate of the extra tidal energy that could be harvested. The power available in a tide is proportional to the square of the height difference between high and low water. If the average range grows from 1.3 meters to roughly 2 meters, the theoretical power per meter of coastline could rise by about 2.4 times. Existing tidal turbines would see a boost in output, but they would also face stronger currents that could increase wear. The new tidal resonances would also affect the timing of the tides. The familiar twice-daily cycle would be modulated by the beat pattern, creating days with 3 noticeable high waters, or occasionally only 1. Mariners who rely on predictable tides would need to adjust their charts, and the old adage, low water at the turn of the tide, would become less reliable. I admit that many of these projections sit on simplified models. Real oceans are messy, with coastlines that break the symmetry of the equations. Numerical simulations would be required to capture the full picture, and those simulations would need to incorporate the new moon's exact mass, orbital eccentricity, and inclination. We don't really know how those details would play out. One concrete observation emerges from a simple instrument. A tide gauge installed on the western shore of the Bay of Fundy recorded a rise of 0.3 meters in a single half-day when the two moons aligned. The extra lunar companion would raise the average high tide by a few centimeters, a modest but persistent push on the ocean's surface. That extra pull would be felt everywhere, from shallow bays to the deepest trenches. When the tide climbs higher, more water is forced into the continental shelves. The added volume changes the density of the surface layer, nudging the delicate balance that drives the global thermohaline conveyor belt. Thermohaline circulation is a slow, gravity-driven engine that moves cold, salty water southward and returns warm water northward. A slight increase in surface salinity, because evaporation now leaves a bit more salt behind, could make that engine spin a fraction faster or stall it in places. I find it hard to picture how a few centimeters of extra water could reshape a system that stretches for thousands of kilometers. Yet the equations that describe buoyancy are unforgiving. Even a tiny density shift can alter the vertical exchange between surface and deep layers. If the Gulf Stream were to lose a few meters per second of speed, the climate of Northeast America would feel the change. Summers might become a degree cooler, winters a shade milder, simply because less heat is carried across the Atlantic. The Kuroshio Current, Japan's counterpart, could experience the opposite. A modest acceleration would push more warm water toward the polar front, nudging the storm tracks that steer winter rains across East Asia. Regional precipitation patterns are linked to these currents through atmospheric rivers, narrow bands of moisture that follow the ocean's heat. A shift in the Gulf Stream's position could move the Atlantic moisture plume inland, altering rainfall over the Midwest. Such a shift would not stay confined to the ocean. The atmosphere reacts to the sea surface temperature field, adjusting wind patterns that in turn feed back on the ocean. It is a loop that can amplify a small tidal perturbation into a noticeable climate signal. Modelers have tried to capture this feedback with coupled ocean-atmosphere simulations. The results scatter widely because the models differ in how they treat small-scale mixing and the response of sea ice. We don't really know which version is closest to reality. One study showed a 5% increase in tidal energy could raise the Atlantic meridional overturning strength by 0.2 SV, 1 Sverdrup. That is enough to shift the position of the North Atlantic subtropical gyre by a few hundred kilometers. The shift would move the core of the Gulf Stream farther east, edging the cold tongue of Labrador closer to Europe. If the cold tongue moves, the temperature gradient between the ocean and the overlying air narrows. The reduced gradient weakens the baroclinic instability that fuels mid-latitude storms, potentially leading to fewer, but more intense, cyclones over the North Atlantic. In the Pacific, a stronger Kuroshio could deepen the subtropical gyre, trapping more heat near the surface. That heat would be released into the atmosphere during the summer monsoon, possibly extending the rainy season over the Philippines. The Arctic is especially sensitive to changes in heat transport. A faster Atlantic inflow of warm water could thin sea ice cover earlier each year, exposing darker ocean that absorbs more sunlight. The extra absorption would feed back into the ocean's heat budget, accelerating the melt. Conversely, if the extra moon's tides dampen the deep water formation in the Labrador Sea, the Atlantic heat pump could weaken. That would leave the North Atlantic cooler, perhaps allowing sea ice to linger longer than it does now. Both scenarios illustrate how a modest alteration in tide-driven mixing can cascade through the climate system. The pathways are tangled, and the timing of each response is uncertain. Observations from satellite altimetry show that current tidal amplitudes already vary by a few centimeters across the globe. Adding another lunar source would broaden that variability, making it harder to isolate natural cycles from anthropogenic trends. Scientists would need to recalibrate tide gauges, re-examine paleoclimate records, and adjust the baseline for future projections. The effort would be a reminder that our climate metrics rest on a fragile set of assumptions. Even the simplest climate indicator, average surface temperature, could wobble more from month to month as the ocean's heat transport fluctuates. That wobble would complicate the detection of long-term warming signals. There is also a practical side. Shipping routes that rely on predictable currents might need to be rerouted. A marginally slower Gulf Stream could add hours to a transatlantic voyage, raising fuel costs and emissions. Fisheries that follow the edge of the Gulf Stream might find their traditional grounds shifting. Species that depend on the sharp temperature front could be forced northward, altering local catches. All of these adjustments would happen against the backdrop of a night sky now split by two moons. The extra light would not change the physics, but it would remind us that the planet's balance can be tipped by something as simple as a change in gravitational pull. In the end, the ocean's response would be a mixture of measurable shifts and subtle, hard-to-track feedbacks. Our instruments would capture the big moves. The small, lingering ripples would be left to the imagination. One of the tide gauges on the coast of Portugal, after the new moon appeared, recorded a high tide that was exactly 3 cm higher than any previous reading for that date. I sit at the desk, notebook open, and write down the first thing that strikes me. An extra lunar mass hanging overhead would add a steady pull on every kilogram of crust. The force is tiny compared to Earth's own gravity, yet it is not zero. When you multiply that extra tug by the planet's 5 × 10^24 kg, you begin to feel a whisper of pressure on the mantle-rock interface. The mantle is not a fluid you can stir with a spoon. It behaves like a very slow, viscous solid, creeping under stress over millions of years. Adding a periodic gravitational component changes the way that creep is distributed. In a lab note style, I would record, observe stress vectors shifting by a few millipascal each lunar day. Cumulative effect may reorient fault zone loading. It is a modest shift, but faults are already perched near failure, like a stack of cards waiting for a nudge. If the extra moon follows the same orbital period as our familiar companion, the tidal bulge would beat twice a day, now with a slightly larger amplitude. The resulting flexing of the crust could raise the background strain by a fraction of a percent. That sounds negligible, but the Gutenberg-Richter law tells us that even a small increase in stress can raise the probability of a slip event. I note a potential rise in the frequency of magnitude 4 tremors, perhaps a few extra per year in regions already active. The magnitude of individual quakes is another question. The slip area on a fault is proportional to the stress drop, and the extra lunar pull could add a few kilopascals to that drop. In theory, a magnitude 6 quake might release a few percent more energy than it would otherwise. In practice, the Earth's crust is a mess of irregularities, and the exact amount is hard to pin down. I find it hard to picture how a moon, sitting 380 km away, could tip a fault that has been dormant for centuries. Historical records give us a hint, though the evidence is fuzzy. Some studies have reported a slight uptick in shallow earthquakes during full and new moons when lunar tides are strongest. Others find no clear pattern. The data are noisy, and the statistical methods differ from one paper to the next. I write, correlation coefficient between lunar phase and seismicity hovers around 0.1, barely above random chance. That does not rule out a subtle influence, but it also does not confirm one. Volcanoes respond to stress in a different way. Magma chambers sit beneath the crust, pressurized by gases and heat. When the surrounding rock is squeezed even a little, the chamber can expand, cracking the roof and allowing melt to rise. A modest increase in lithostatic pressure from the extra moon could nudge a marginally stable system over the edge. Dormant volcanoes that have not erupted for millennia might feel that nudge as a faint, persistent push. In the laboratory, we simulate this by applying a uniform load to a rock sample and watching microfractures appear. The experiments show that a load increase of just a few percent can double the rate of acoustic emissions, a proxy for crack growth. Translating that to a whole volcano is speculative, but the analogy suggests that the extra lunar pull could raise the background eruption probability by a small amount. I note a possible increase of 0.1% in eruption frequency for volcanoes already near critical stress. Our current geophysical models struggle with these nuances. Most seismic hazard simulations treat the moon's tide as a secondary, periodic term, not a driver of long-term stress evolution. The equations assume linear elasticity, whereas the Earth's crust behaves non-linearly under high strain. Adding a second moon would require recalibrating the tidal potential, but the data to validate such a model are missing. I write, model uncertainty dominates. We cannot claim a precise forecast for quake or eruption rates. Even the simplest estimate runs into limits. The extra moon's mass is unknown. If it were comparable to our moon, the tidal amplitude would roughly double. If it were smaller, the effect would be proportionally less. Without a mass, any number I put on stress change is a guess. I find it hard to picture the exact magnitude of the pull without an orbital solution. There is also the matter of timing. The Earth's rotation and the moon's orbital periods would create a complex beat pattern. Some locations might experience a reinforcement of tidal stress every few weeks, while others see a cancellation. The pattern could be mapped, but the mapping would be a mosaic of high and low stress zones shifting over the globe. I note that the stress field would become more heterogeneous, perhaps concentrating strain along certain fault segments. If strain concentrates, those segments could become more active, while others quiet down. The net global earthquake count might stay roughly the same, but the distribution could shift. A region that has been relatively calm for centuries could see a sudden spike in activity, simply because the extralunar pull aligns with its fault orientation. That would be a striking, localized change. One could argue that the mantle's viscosity would damp out any short-term variations, smoothing the stress over thousands of years. Yet the crust reacts on much shorter timescales. The elastic rebound that follows a quake happens in seconds. The extralunar component adds a quasi-static bias to the stress, not a sudden shock, so the mantle's damping does not erase the bias. I write, static bias persists. Dynamic damping is limited. The uncertainty is large, and the models we have are built for a single moon scenario. Adding a second body forces us to re-examine assumptions about stress equilibrium. It is a reminder that our picture of the Earth's interior is provisional, a sketch that works well enough for most purposes but cracks under new constraints. We don't really know how the crust would settle into a new balance. In the field, seismologists would look for subtle changes in the background noise level, tiny tremors that never reach the detection threshold for cataloging. An increase in that micro-seismic hum could be the first sign that the extralunar pull is reshaping stress pathways. I imagine a network of broadband sensors, their needles trembling ever so slightly as the planet's skin flexes under an unfamiliar weight. Volcanologists would monitor gas emissions and ground deformation with the same cautious eye. A slight uptick in sulfur dioxide or a few millimeters of uplift on a volcano's flank could indicate that the magma chamber is feeling a new pressure regime. Those measurements, taken together with seismic data, would form a tentative picture of the Earth's response. The bottom line, as I write it, is that an additional lunar mass would not cause the planet to shatter, but it would tweak the stress budget that drives earthquakes and eruptions. The tweak is small, perhaps only a few % of the total stress, yet the Earth's fault system is poised at the edge of failure. A nudge, however gentle, can change which edge finally gives way. I close the notebook with a single observation. The crust beneath the Pacific Ring of Fire would feel a fraction more pull during each high tide, a whisper of extra weight that could, over years, shift the timing of a tremor by a few seconds. That tiny shift, recorded in a seismogram, would be the only clue we have that the sky has changed. The lunar pull on our atmosphere is faint, but it is measurable with the right instruments. When a second moon appears, that pull doubles in places and cancels in others, reshaping the very rhythm of the air above us. I find it hard to picture a sky where two silvery disks tug at the same layer of gas, yet the physics does not refuse the idea. Lunar atmospheric tides arise because the moon's gravity stretches the whole column of air, much like it stretches the oceans. The effect is strongest near the sub-lunar point, where the line from Earth's center to the moon meets the surface. There the atmosphere bulges upward by a few millimeters, then sinks elsewhere. This vertical motion repeats every 12 hours and 12 minutes, matching the moon's orbital period. It is a diurnal pattern, slower than the solar heating that drives daytime heating tides. Solar diurnal tides dominate the daytime heating of the atmosphere, producing a pressure wave that climbs from the ground to the stratosphere. They peak at local noon and midnight, creating a familiar 24-hour rhythm. When a second lunar mass joins the dance, its own tidal wave interferes with the solar one. In some longitudes, the two lunar contributions align, amplifying the pressure oscillation. In others, they oppose, damping it. The net result is a patchwork of stronger and weaker tides that shift with the relative positions of the two moons. The jet streams, those narrow ribbons of fast-moving air high above the surface, are sensitive to any change in pressure gradients. Their paths are guided by the balance between the equator to pole temperature contrast and the Coriolis force, but they also respond to the subtle push of atmospheric tides. A reinforced lunar tide can nudge the upper tropospheric wind field, causing the jet core to drift a few degrees north or south. Over weeks, these small displacements may alter the preferred tracks of mid-latitude cyclones. Storm tracks, in turn, follow the jet streams. If the jet shifts, the zones where storms intensify and decay also move. A region that normally sees frequent winter lows might experience a lull, while another area could see a sudden uptick in storm frequency. The change would not be catastrophic, but it would be noticeable in the seasonal statistics that meteorologists keep. It does not quite make sense when you say it aloud. A new moon, a new pattern of rain. Aviation already contends with jet stream variability, using forecasts to plan routes that save fuel. A double moon scenario would add another layer of uncertainty. Pilots might encounter stronger tailwinds one day, then weaker ones the next, without a clear seasonal pattern. The altered tidal pressure could also modify the density of the upper atmosphere, affecting aircraft performance at cruising altitude. Even a change of a few kilograms per cubic meter can shift climb rates by a fraction of a percent, enough to matter on tight schedules. Satellites orbit in the thin exosphere where atmospheric drag is a slow but steady force. The drag depends on the density of the residual gases, which in turn follows the tidal bulge. When the lunar tide lifts the atmosphere, drag increases. When it depresses the atmosphere, drag decreases. With two moons, the drag cycle would acquire a secondary peak, potentially shortening the orbital lifetime of low Earth satellites by weeks or months. Operators would need to adjust re-entry predictions more frequently. Detecting these atmospheric changes requires precise, continuous measurements. Ground-based barometers can record pressure variations down to a few pascals, but they are influenced by local weather. A network of high-altitude radiosondes launched twice daily can map the vertical structure of the tide. LiDAR stations, pointing lasers upward, can track the density of the mesosphere with millimeter resolution. Space-borne limb sounders, looking at the edge of the atmosphere, provide a global view of the tidal wave as it propagates around the planet. One promising strategy is to combine the data streams into a tidal model that isolates the lunar component. By subtracting the well-known solar diurnal tide, the residual should reveal the pattern imposed by the moons. The model must account for the relative positions of both moons, which will produce a beat frequency as they orbit at slightly different rates. That beat could manifest as a slow modulation of the tidal amplitude over weeks. We don't really know how large the atmospheric response would be. The oceanic tide under a double moon scenario can be estimated from the gravitational equations, but the atmosphere is far less dense and more compressible. Some early calculations suggest a pressure change of up to a few tenths of a pascal at the surface, rising to several pascals higher up. Those numbers are small compared with everyday weather fluctuations, yet they are systematic and repeatable. If the pressure wave reaches the stratosphere, it could affect the distribution of ozone by moving air parcels vertically. The ozone layer is a thin shell that absorbs ultraviolet radiation, and its chemistry is sensitive to temperature and pressure. A modest shift in the vertical motion might alter the timing of ozone transport, with downstream effects on surface UV levels. The chain of cause and effect quickly becomes tangled, and the uncertainties multiply. The double moon effect would also be felt in the ionosphere, where the charged particles respond to both solar radiation and the underlying neutral atmosphere. Tidal winds can modulate the electron density, influencing radio communication and GPS accuracy. A new lunar tide could introduce a secondary peak in the ionospheric electron content, complicating the correction algorithms that navigation systems rely on. From a practical standpoint, the most immediate concern for daily life would be the slight change in weather patterns. Farmers might notice a shift in the timing of the first frost, or a coastal town could see a different pattern of sea breeze onset. Those changes would be gradual, not a sudden storm, but they would be measurable over a season. In the laboratory, researchers could simulate the double moon tidal forcing using rotating tanks of fluid, adjusting the rotation rate to mimic the lunar periods. By adding a second, out-of-phase forcing term, they can observe how the wave patterns interfere. The experiments would not capture the full complexity of the real atmosphere, but they would offer a tangible picture of the interference. Observatories that monitor the Earth's shape, such as those using satellite laser ranging, already detect the tiny bulge caused by the moon's gravity. Adding a second moon would double the amplitude of that bulge in certain orientations, providing an independent check on the atmospheric models. The geodetic signal would be small, but the precision of modern instruments can resolve changes of a few millimeters. On a clear night, the two moons would rise and set at different times, casting overlapping shadows on the atmosphere. The twilight glow might display a faint, double-crested band where the lunar tides compress the air, a subtle shimmer against the dark sky. It is a detail that could be recorded by all sky cameras, adding a visual cue to the pressure measurements. The most reliable way to confirm the atmospheric tide would be to look for a consistent phase relationship between the pressure data and the lunar positions. If the pressure peaks line up with the sub-lunar points of either moon, the link is established. If the peaks drift, the interaction is more complex, perhaps dominated by the beat frequency. Either outcome would refine our understanding of how celestial bodies shape the air we breathe. A final, modest observation. A low-orbit satellite passing over the Pacific during a lunar conjunction recorded a minute increase in drag, enough to lower its altitude by a few centimeters over a single orbit. The data point sits in a sea of numbers, but it hints at the subtle hand of a second moon on the thin veil above us. When the second moon rose, the night seemed heavier, its extra glow pressing on the shore. I noted the immediate confusion in the crabs scuttling across the sand. Many marine animals time spawning to the lunar cycle, using moonlight as a distant clock. A twin moon would double the light, blurring the signal they have learned to trust. Coral reefs, for example, release gametes a few nights after the full moon. If two full moons overlapped, the timing cue could shift by hours or disappear. Grunion fish in California beach pools wait for the brightest night to sprint onto sand. With an extra lunar peak, the hatchlings might emerge too early, drowning in retreating water. Sea turtles navigate to nesting beaches by moonlit horizons, a practice honed over millennia. A second moon would add a second horizon, potentially sending them off course by degrees. Researchers have recorded turtles circling under a single moon, then correcting after a brief pause. I find it hard to picture how they would decide which glow to follow. Nocturnal mammals, such as bats, use lunar brightness to gauge insect activity. Two sources of light could mask the subtle dimming that signals prey emergence. Owls, which rely on moonlit silhouettes to locate rodents, might misjudge distances. A miscalculation of even a few meters could turn a successful hunt into failure. Many insects synchronize emergence with the first quarter moon, using its waning light as a cue. If two moons reach quarter simultaneously, the cue could become ambiguous, spreading emergence over days. Plants in coastal dunes often flower when moonlight reaches a certain intensity. An added source of illumination might trigger premature blooming, exposing buds to frost. Some algae species adjust photosynthetic cycles to the lunar night, conserving energy during darkness. Two alternating dark periods could confuse this balance, perhaps reducing growth rates. I don't really know how quickly a population could shift its internal clock. Laboratory experiments with altered light cycles suggest plasticity, but field conditions are harsher. Genetic adaptation may eventually produce a new rhythm, but that would take many generations. In the meantime, mismatched timing could cause temporary drops in reproductive success. Case studies of lunar-sensitive species show that even small changes in moon phase can alter behavior. When lunar illumination shifts by a few percent, some fish delay spawning by days. If a second moon adds 30% more light, the delay could extend to weeks. Weeks of mistimed breeding could ripple through food webs, affecting predators and scavengers alike. Marine plankton, the base of many oceanic diets, also respond to lunar cues. A double lunar signal might shift their vertical migration, altering nutrient transport. Such a shift could reduce the food available to filter-feeding bivalves. Bivalves, in turn, provide habitat for countless small organisms, so the effect multiplies. On land, many amphibians breed in response to moonlit rains, timing egg-laying to darkness. An extra moon could make nights brighter, possibly discouraging some species from laying eggs. I find it hard to imagine a frog chorus under two full moons, each echoing. The chorus might split, some individuals answering one moon, others the second, creating a disjointed pattern. Bird migration often relies on lunar navigation, especially for nocturnal migrants crossing oceans. A second moon could generate conflicting magnetic cues, leading to increased straying. Studies of night-flying insects show they orient toward the brightest lunar point. When 2 points share equal brightness, the insects may wander aimlessly, reducing pollination rates. Pollinator decline would affect plants that depend on nighttime visitors, such as certain cacti. Cacti that open flowers under moonlight could see fewer fertilizations, limiting seed set. In some temperate forests, leaf drop timing aligns with the lunar cycle, reducing herbivore exposure. A disrupted lunar cue could cause leaves to linger, making seedlings more vulnerable. I don't really know whether such a shift would be enough to alter forest composition. Long-term data are lacking, and we can only extrapolate from short experiments. Some species show rapid behavioral flexibility. Urban birds adjust song timing to artificial lights. If they can cope with human lighting, perhaps they could also learn to read a new lunar schedule. Yet many organisms lack such plasticity, especially those with fixed hormonal triggers. Hormonal cascades tied to a single moonrise may falter when the sky offers two. The cascade effect can be visualized as a chain of mismatched clocks. When one link ticks faster, the whole system loses synchrony and energy flow stalls. Field biologists have recorded coral bleaching events linked to lunar misalignment, though causality remains unclear. Adding a second moon would amplify the misalignment, potentially increasing bleaching frequency. Marine mammals such as dolphins use lunar illumination to coordinate group hunting at night. If the light pattern becomes erratic, coordinated attacks may break down, reducing feeding efficiency. I find it hard to predict the net effect on oceanic carbon uptake. Reduced feeding could lower respiration rates, but also diminish carbon export via fecal pellets. On land, nocturnal pollinators like moths may alter flight paths under dual illumination. Altered routes could change pollen transfer networks, subtly reshaping plant reproductive success. Some desert rodents use moon phases to gauge predator risk, staying hidden on brighter nights. 2 moons would keep nights bright longer, possibly suppressing foraging and affecting population growth. Laboratory work with controlled light cycles shows that some species can reset their internal clocks within weeks. Whether wild populations could achieve the same reset under a permanent double moon remains uncertain. Adaptation might involve shifting reproductive timing to the interval between the 2 moons, a novel rhythm. Such a shift would require genetic changes to hormone production, a process that rarely happens quickly. If a subset of the population adopts the new schedule, it could eventually dominate the gene pool. But the transition period could be marked by lower reproductive output and higher mortality. The ecological ripple effects would be subtle at first, then perhaps cascade into larger disruptions. A cascade that begins with a single mistimed spawning event could echo through the food chain. We lack long-term observations of ecosystems under 2 moons, so any projection stays speculative. What we can say is that lunar cues are woven into the biology of countless species. Tonight, a lone firefly flickered beside a second moon, its glow a faint, steady pulse. The night sky, once familiar, now bears 2 silvery disks that rise together over the horizon. People stare, then whisper, then turn their backs to the bright, uneasy glow. Artists already accustomed to a single lunar muse scramble for new symbols. Paintings begin to show twin crescents overlapping, a motif that spreads from street murals to high-end galleries. Poets, half amused, half confused, insert the second moon into verses that once counted 12 months. I find it hard to picture a sonnet that fits both moons without sounding forced. Myths, those old scaffolds of meaning, reshape overnight. In coastal villages, elders tell stories of twin spirits tugging at the sea, explaining sudden floods as a celestial quarrel. Children repeat the tale, clutching at the idea that the heavens can argue. The narrative spreads, mutating as it moves inland but always keeping the twin moons at its core. Farmers, whose calendars were once synced to the lunar cycle, now face a confusing rhythm. Planting dates, traditionally marked by the full moon's rise, become ambiguous when 2 full moons appear in a single month. Some adopt a compromise, using the brighter of the pair as the marker. Others switch to solar cues, abandoning the moon altogether. The result is a patchwork of practices that complicates market forecasts. Fishermen, too, feel the shift. Tidal patterns, altered by the added gravitational pull, change the timing of fish migrations. Nets that were lowered at low tide now miss their catch because the low tide arrives earlier or later than expected. Local cooperatives experiment with new tide tables, but the data is noisy, and many admit they don't really know how reliable the predictions are. Coastal engineers stare at blueprints, the second moon's pull evident in every calculation. Sea walls that once withstood a predictable surge now confront a higher, more erratic maximum. Reinforcement plans emerge. Thicker concrete, deeper pilings, flexible joints that can absorb unexpected pressure. Yet budgets already stretched strain under the added expense, and some municipalities postpone upgrades, hoping the anomaly will fade. Navigation, a discipline built on the steady guidance of a single moon, must be rewritten. Sailors who once used lunar position to estimate longitude now receive conflicting signals. Modern GPS systems remain unaffected, but traditional mariners cling to the old methods, feeling a loss of identity. Chart makers add a new column for secondary lunar bearing, but the column remains mostly blank, a reminder of the uncertainty. Timekeeping, too, faces a subtle but persistent revision. Calendars that counted 13 lunar months in a year now contain 14, if the second moon's cycle is taken seriously. Religious festivals that align with the full moon shift dates, causing confusion in communities that tie ritual to lunar phases. Some leaders propose a dual calendar system, but the administrative load proves cumbersome, and many simply ignore the second cycle. Psychologically, the altered night sky exerts a quiet pressure. Nighttime, once a period of dimmed activity, now glows brighter, extending the day's visual reach. Insomniacs claim the extra light makes sleep harder, while others say the twin moons create a feeling of perpetual observation. Surveys show a slight rise in anxiety levels, especially among those who grew up with a single, predictable moon. Cities adapt their lighting to the new luminescence. Streetlights dim in neighborhoods where the twin moons provide enough illumination, saving energy but also altering the character of nocturnal streets. Residents notice the shadows shifting in unfamiliar ways, the familiar silhouette of a lamppost now split by two overlapping halos. Cultural festivals, which once celebrated the harvest moon, now feature processions under both moons. In one town, a double moon dance emerges, choreographed to mimic the orbital dance of the two bodies. The event draws tourists, injecting cash into the local economy, yet also sparking debate about authenticity versus spectacle. Education systems revise textbooks overnight. Science classes add a chapter on binary lunar systems, while art classes assign projects to reinterpret classic lunar myths. Teachers admit they had no prepared lesson plans, and many rely on last-minute research that may contain errors. The media, always eager for a hook, floods the airwaves with speculation. Talk shows host astronomers who argue over whether the second moon is a captured asteroid or a temporary optical illusion. Viewers, fatigued by the constant chatter, tune out, leaving a quiet hum of background commentary. Even language bends. Phrases like "once in a blue moon" acquire a new twist as people joke about "once in a double moon." The expression spreads, but its original meaning, something rare, now feels oddly literal. Governments tasked with maintaining order draft policies to address the new reality. Maritime law, for instance, incorporates clauses about dual tidal forces when assigning rescue responsibilities. The legislation, drafted in haste, contains ambiguities that lawyers will later argue over in courtrooms. Economically, the ripple effects are uneven. Tourism booms in regions where the twin moons are visible, while agricultural exports from areas struggling with altered tides decline. Trade balances shift, prompting a modest reallocation of resources, but the long-term impact remains uncertain. People find comfort in small, personal rituals. Some set up 2 lanterns on their balconies, aligning them with the moons each night. Others write diary entries noting the exact time each moon rises, creating a private record of the sky's new rhythm. The act of observation becomes a quiet anchor in an otherwise shifting world. Even the night's soundscape changes. Crickets, which normally chirp in response to lunar illumination, adjust their calls, producing a layered chorus that seems to echo the twin lights above. The altered rhythm of insects goes unnoticed by most, but those who sit outside at midnight can hear the subtle difference. In the end, the second moon does not rewrite humanity overnight. It nudges habits, reshapes stories, and adds a faint strain to the fabric of daily life. A fisherman in a small port watches the twin silhouettes reflect on the water, noting how the larger moon's glare makes the fish scales glint a little brighter. The idea of two permanent satellites circling Earth feels like a lab note written in the dark, half finished, the ink still drying. I start by asking whether gravity alone can keep such a pair together for millions of years, or whether the system is doomed to dissolve. First, the two moons would settle into an orbital resonance, a repeating pattern of positions that locks their periods together. In our solar system, the Galilean moons of Jupiter show a 1, 2, 4 resonance that has survived for eons. That stability comes from precise ratios. Any deviation nudges the orbits, slowly draining energy. If our new companion fell into a resonance with the existing moon, the exchange of orbital energy would be continuous, not a single jolt. The exchange itself is a transfer of angular momentum. The larger moon already carries most of Earth's rotational momentum, slowing our day by about 2 milliseconds per century. A second body would either steal some of that momentum or give it back, depending on its distance and mass. If the newcomer orbited closer, it would tug harder, pulling Earth's spin down faster. If it lingered farther out, it might actually return a fraction of momentum, lengthening the day slightly. The net effect would be a slow drift, measurable only after many generations. I find it hard to picture the exact path of that momentum flow. The mathematics demands solving coupled differential equations that change as the moons migrate. Small uncertainties in mass or initial speed cascade into large differences after a few 100,000 years. In practice, we would need a computer model that updates every orbital pass, and even then the result would be a range, not a single answer. Even with a resonance, the pair is vulnerable to orbital decay. Tidal forces raise bulges on Earth, and the same bulges pull back on the moons, draining orbital energy. The classic single moon case shows the satellite spiraling outward at a few centimeters per year. Add a second and the bulges become more complex. The net tidal torque could increase, accelerating the outward drift of both bodies, or it could create a tug of war that forces one inward. If one moon slips inside the synchronous radius, it would begin to fall, eventually crashing into Earth or breaking apart. A collision between the moons is another plausible endpoint. In a binary dwarf system like Pluto-Charon, the two bodies are locked in a mutual orbit that never leads to impact because their masses and distances are finely balanced. Earth's moons would be far less massive, and the resonance could drive their orbits to intersect. A slow, glancing encounter might eject one moon into a solar orbit, while a direct hit could shatter both into a ring of debris. That debris would then rain down as a prolonged meteor shower, altering surface conditions for centuries. Observations of binary asteroids give us a glimpse of how fragile such arrangements can be. Many small binaries are held together only by a tenuous gravitational handshake. A slight perturbation from a passing planet can separate them. Earth's gravity is stronger, but the principle remains. A third body, perhaps a passing comet or even the Sun's own pull at perihelion, could tip the balance. The system would then lose one moon, either flinging it outward or sending it spiraling inward. If a moon were lost, Earth's rotational period would adjust again. The day length is tied to the total angular momentum of the planet-moon system. Losing a satellite removes a chunk of that momentum, causing the planet to spin up slightly. The change would be minuscule, maybe a fraction of a second over a millennium, but over geological time it could shift climate cycles that depend on day length. It is a reminder that even tiny shifts accumulate. One might wonder whether Earth could ever settle into a permanent double moon configuration, like the binary dwarf pair that has persisted for billions of years. The key difference lies in mass ratios. Pluto and Charon share roughly an eighth of each other's mass, making their barycenter sit outside Pluto's surface. In Earth's case, the new moon would be far smaller than our current one, so the barycenter would stay well within Earth. That asymmetry makes the system more prone to drift, because the dominant moon continues to dominate the torque budget. The long-term picture, then, is a slow dance that may end in separation rather than permanence. Orbital resonances can hold for a while, but tidal dissipation, angular momentum exchange, and external perturbations act like a subtle friction that erodes the pattern. Over tens of millions of years, the most likely outcome is either a gradual widening that pushes one moon beyond Earth's Hill sphere, or an eventual collision that reshapes both bodies. We don't really know which path would dominate without running a suite of simulations that span billions of years. The uncertainties in initial conditions, mass, eccentricity, inclination, are too large to pin down a single fate. What we can say is that a double moon system would be a temporary phase in Earth's dynamical history, not a stable end state. In the quiet of a nighttime observatory, a seismometer recorded a faint, regular tremor that matched the beat of the new moon's orbit. The tiny vibration lingered, a reminder that the planet still feels the pull of its unexpected companion. The night sky has always been a ledger of forces we cannot touch, only read. When a second disk of reflected sunlight appeared, the ledger suddenly doubled its entries, and the ink seemed to run. I find it hard to picture how the planet's wobble would settle after such a shock. The extra pull would tug at the oceans, at the mantle, at the atmosphere, each layer feeling a new rhythm. In a lab note style, I would record the first tide that rose 3 meters higher than the chart allowed, then note the shoreline sigh as sediment slipped away. The immediate lesson is simple. The dance of planets and satellites is not a distant abstraction. It is a chain of pressure, of weight, that reaches into the soil where roots drink, into the veins of rivers that carve valleys. One extra moon would rewrite that chain, and the rewrite would be felt in the smallest plankton bloom as well as in the largest fault line. Speculative scenarios like this are uncomfortable, but they are useful. They force us to ask, what if our assumptions about stability are wrong? The answer, in my notebook, is a list of contingencies that never made it past the draft stage. We don't really know how quickly a new orbital resonance could destabilize the axial tilt, but we can sketch the possible outcomes and keep the sketches on the shelf for future reference. When we map the habitability of distant planets, we often count the number of moons as a footnote. A double moon would push that footnote into a paragraph, reminding us that habitability is a balance of many forces, not a single metric. A planet that seems perfect from afar may hide a fragile equilibrium that a sudden change could shatter. The double moon thought experiment nudges us to widen the lens, to see habitability as a web rather than a point. In the weeks after the appearance, astronomers would train every available telescope on the new companion. Spectra would be taken, orbital decay measured, surface albedo compared. Those data would become a new class of observation, a reminder that the sky can rewrite its own script without warning. The instruments would capture the faint glow of reflected Earthlight on the new moon's far side, a detail that would sit in a data table next to a note about the altered lunar libration. I keep returning to the idea that everything is linked. The extra gravitational tug would change the precession of the equinoxes, shifting the timing of seasons by minutes each year. Those minutes add up, and over centuries they could alter the growth rings of trees, the migration patterns of birds, the timing of monsoons. A single orbital addition ripples through climate, through biology, through culture, because the forces are shared. The value of speculative work is that it keeps the mind alert to low probability, high-impact events. In a lab notebook, I would write a margin note: prepare for the unexpected. Keep models flexible. It is not a panic prescription, just a reminder that our equations are only as good as the assumptions we dare to test. Future observational opportunities would not stop at the new moon itself. The altered tides would expose previously hidden seabed features, allowing geologists to sample rock that has lain undisturbed for millennia. Biologists could watch how coral reefs respond to a sudden change in water motion, gaining insight that may apply to climate-induced stress elsewhere. Each of those chances would be a quiet proof that a dramatic celestial change can open a window on processes we otherwise study only in slow motion. The broader perspective that emerges is humbler. We have long measured our place by the number of stars we can count, by the size of our atmosphere, by the richness of our biosphere. Adding a second moon forces us to reconsider the fragility of that place. It is a reminder that the conditions we enjoy are the product of many synchronized motions, each one able to tip the scale. In the margins of my notes, I sometimes write a question that feels almost philosophical. If a planet can survive a sudden extra satellite, what does that say about the range of conditions that might support life elsewhere? The answer is not a neat conclusion, but a series of maybe statements that sit beside the raw numbers. It is a small step toward a broader view of planetary habitability that includes the possibility of sudden, unpredictable changes. Humanity's response would be a mix of awe and practical adjustment. Coastal cities would reinforce flood defenses, farmers would alter planting calendars, engineers would re-evaluate the stress on bridges that now face higher tidal ranges. Those actions would be recorded not as triumphs, but as adaptations to a new baseline, a baseline that was never part of the original plan. I admit that my notebook cannot capture every ripple that a double moon would cause. Some effects would be too subtle to notice until centuries later, buried in the layers of ice or in the genetic code of long-lived species. The limits of our current models mean we can only sketch the outline, not fill in every detail. Yet the act of writing, of putting the scenario on paper, does something else. It sharpens our awareness of the interconnectedness that binds celestial mechanics to the breath of living things. It reminds us that the pull of a distant rock can change the pressure on a leaf, that a shift in orbital resonance can alter the timing of a river's flood, that a new lunar face can reshape the night's glow over a desert camp. Future telescopes will likely watch the new moon's orbit decay, or perhaps its gradual drift away. Those measurements will be logged alongside the first recorded shift in the length of a day, a few milliseconds longer than before. In the quiet of a control room, a technician might note the faint hiss of a data logger as it captures the moment the moon's shadow grazes a mountain ridge for the first time. When I close the notebook for the night, the page is still warm from the ink, the words a thin layer over the uncertainty. The sky outside is unchanged in its darkness, but the extra disk hangs there, a silent reminder that the balance we rely on can be altered with a single, unexpected addition. A single grain of sand, caught in the tide, glints as the new moon's light catches its edge, an ordinary detail that now belongs to an extraordinary ledger.